Okay, I'm going to ask you, say it again. That was going to be my first question. Thanks. Okay, so let's start. Okay, so first I hope that all of you enjoyed Daniel's lectures last week on neural networks. I already heard, I appreciate the feedback that it was good, but if you want to say something or send me feedback, it's always good to send feedback, but specifically in this case, I'm sure that he'll be happy to get feedback from you, and I'm happy to send it. That's one. Two, we are actually changing gear today, so we're moving to, it's really the third part of the semester, but kind of the second half conceptually. But I want to start with a few administration things. So one, exam. So the exam will be in class. The last meeting, which I think is April 24, short exam, so 75 minutes, similar to the previous one, closed book, everything is the same. What is going to be covered? So really the focus is going to be on what we've done since the midterm. However, I'm going to mislead you if I tell you that it's going to be disconnected from the first part, because there's no way to disconnect it. We're talking about the same thing. And as you will see, and you already have seen, hopefully in the last few weeks, everything is connected. So we're always going back to ideas that we introduced at the beginning and building on them. And we're going to continue to do it. So the ideas are cumulative. There's no way to avoid it. Make sure that you understand this. We will give several practice exams as we did in the midterm. But hopefully this will allow you to figure out what we're going to cover and what kind of questions we're thinking of. One important thing is what is the material. So everything we present in the slides, is covered. There is a lot of other material in the slides that I don't talk about. It's not covered. So I'm not going to require that you know things that I did not talk about in class or that were not mentioned in the homework assignments. What I talked about, what's in the homework, that's fair game. So specifically, I'm referring here to questions that people have asked. One, we talked about boosting, other boost. You need to know that. We did not talk about boosting the confidence, for example. If you remember, boosting is really boosting the error, the epsilon. We did not talk about boosting delta, even though there's slides on it. I don't require that you know this. We talked about multi-class classifications. I covered in class one versus all versus all. There's a few other interesting things in the slides that I did not touch. Error correcting codes, constraint classification. You don't need to know that. You can read it, but it's not part of the material. I'm sure there are other exams. Other examples of that. Questions? Okay, if you do have questions, please do ask on Piazza or office hours. 2, projects. This involves only about 2/3 of you or something like that, but still important. So we're going to have a poster session. I think poster sessions are really fun events because it gives all of you the opportunity to see what other people are doing. In such a large class, it's impossible to do presentations. So posters is a pretty good, maybe even better way to do it. Given many requests to either push it as much as possible to the future or do it as early as possible, eventually we caved in and we did a poll. 72% of those of you that voted prefer the later date, so that's what we're going to do. I know that some of you don't like it, but you know that's better for the vast majority of people. As I said, I think it could be a fun event. You know, everyone, even 419 students that don't do projects, are welcome to come and see what's happening. I already know that some of you are doing really, really nice projects, so I'm excited about what's going to happen there, and hopefully you will enjoy too. The logistics, which we're going to clarify and make a little bit more concrete, is you're going to send us posters probably a day before because it takes time to print 30 posters. We'll print it for you and hang it for you. You will come and present it. We will go around and hopefully enjoy it. If you haven't done so already, please come to my office hours to talk to me about the projects. So about half of you, half the project have done it, not all. So all the office hours are fair. If you cannot make the office hours, I can stay or schedule some other times. Questions? No questions today. What's happening? You're awake? Yes?
I was wondering if you could talk about what the homeworks will be for the rest of the semester.
There are going to be 2 more homeworks. One of them is going to be on naive Bayes and EM, semi-supervised learning, stuff that we're starting today. And the last one probably about clustering, dimensionality reduction, hasn't completely been decided what it's going to be. We're also going to change the dates a little bit because I'm slower than I thought I will be. But basically, the timetable is about right. Other questions? Okay. So, so what have we done so far? We can think about what we've done as error-driven learning. Because a lot of the algorithms really were driven, even if it's not online, by how well are we doing on a given data. So the general paradigm was we had a distribution over the space x cross y, x instances, y labels, and we could think about the data generation process as something that is being governed by some distribution over x, and then there is a labeling process that governs by distribution d of y given x. So this is a very general way to think about it. You can think about it both in the case that there is actually a function, y equal f of x, that labels the data, or there is some other process, maybe probabilistic generation of the label that assigns each x that is being observed with a label. Now, it's important to realize that there is a distribution that governs the generation of the data, but we don't know it. Had we known it, there's no learning problem, right? So we can do whatever we want. We can predict the label for a given x, basically by doing what I'm writing here under predict. Compute the probability, if you want, of y given x, do argmax over all y's, and that's your prediction. Or if you don't care about the prediction, but rather the function itself, the hypothesis, you can do the same thing with the hypothesis. You're going to compute this hypothesis that minimizes the probability of mislabeling the example. So basically you're going to do argmin over the expected error of your hypothesis. So in our case, we have to assume that we don't know the distribution. Okay, so there are really two basic approaches if we want to think about learning them. One of them is what is called discriminative learning. I'm going to call it here direct learning. And the second one, which we're going to start playing with today, is Bayesian learning, which is also called generative learning. I'm going to use this as an example for the next two slides. Again, this context-sensitive spelling mistake. I saw a girl eat the park, or I saw a girl in the park, and I want to know which sentence is correct, or how to correct a sentence. So in the first paradigm, basically we're learning directly how to make a prediction. And the paradigm is look at many examples, positive and negative examples. In this case, positive and negative examples of the usage of it and in sentences. Discover some regularities in the data. These, of course, depend on how you represent the data. All this business of representation, feature extraction, and so on. And use these to construct a prediction policy. For example, a prediction policy, which is basically, think about it as a function or a predictors, it's going to be very specific. It's going to tell me the prediction policy could be something like this. If the word D occurs after the target, say that the word is in. In practice, it may be a little bit more complicated than just if the word D occurs after the target. It will be a lot of other conditions, or maybe a linear combination of conditions, or maybe some other complex functions of conditions. But it's going to be some function that makes a decision, should it be in or should it be it. The assumption that we are making, because we have to make assumption, this is second lecture that showed that with no assumption there's not going to be learning. The assumptions come in the form of the hypothesis class. Which set of functions are we considering? Which set of classes are we choosing from when we learn? So really the bottom line is that we are approximating a mapping h from x to y by estimating the probability of y given x. That's what we're learning, trying to estimate p of y given x. And we did it in many, many ways, right? So we given a sample, a generic formulation was to choose a loss function, L of xy, and then find a function, h, lowercase h, that minimizes the empirical error under this loss function, which is what's written up here. And then we figured with time, this is how we started, and we figured out that we might as well add also a regularizer here, and we also know why. And we played with multiple L's, and you played with more L's in the problem sets. And what we know is that we have some guarantees for this paradigm. We know that if we find an algorithm that minimizes the loss on the observed data, learning theory guarantees that it's going to be okay in the future. And these guarantees are a function of the size of the hypothesis space. Okay. What happens with the generative case? In this case, really, we model the problem of text correction, not as correcting the text, but rather as of generating correct sentences. So, in fact, what we are doing is we are learning we're learning a model of the language, and then we use it to decide which of the sentences, the one that contains the it or the one that contains the in, is more likely. And that's how we choose. sorry. So really we learn a probability distribution, and then, as I said, use it to choose which one is more likely. Whether the probability under the model that we learn of I saw a girl eat the park or I saw a girl in the park is higher. In practice, what assumptions are we making here? We're going to make assumptions on what is the probability distribution or what types of probability distribution could govern the generation of the data. But really we care about the whole probability distribution. So the generating paradigm approximates P of xy, the joint probability distribution over x and y. And the guarantees are coming from the fact that we choose the right family of distribution. If we choose the right family of distributions, we're likely to find a good member in it. So the family of distribution, in some sense, replaces the set of hypotheses. Now, it's called generative because we really make assumption also on how x is generated given y, the data itself. While in the discriminative thing, we don't care about x, we care about what is the conditional probability of y given x. So this is kind of a conceptual shift, even though, as we'll see, in practice, all the tools that we're going to use are going to be very similar. And in fact, even the guarantees will eventually converge to be very similar guarantees. One clarification that I want to make, because there's sometimes confusion about it, is when we talk about probabilistic learning, there are really two different notions. You can learn probabilistic concepts. By probabilistic concept, I mean here a function that maps x instances to a number between 0 and 1 that can be interpreted as a probability. For example, the probability of x being correct. Now, you can use learning theory, the same type of learning theory that we described earlier, to do this. It's true that everything that we talked about was about Boolean concepts, binary functions. Linear separators was one example, but everything was binary because the VC dimension, for example, that was the basis of our generalization theory, was for Boolean functions. Everything can be generalized. I'm not talking about it, but it can be generalized to multiple output values, any discrete function, and also to continuous functions. So everything we said can be used using Peck learning theory, for example, to learn probabilistic concepts. On the other hand, there's Bayesian learning, where we are using a probabilistic way to choose the hypothesis. We are Bayesian about, and you'll see what I mean when I say we are Bayesian about later today, about how we do the learning. So the hypothesis itself could be deterministic. It could be a Boolean function. It could be a simple rule. But we are Bayesian about how we choose the hypothesis. So really, the important thing to understand, it's not the hypothesis that makes a difference. It's the process, the learning process that is different between discriminative learning and generative learning or Bayesian learning. And that's what we're going to talk about today. Okay. So I'm going to take a very short detour and talk a little bit about probability theory. I assume that for some of you, it's going to be old news because you've seen it before and you're fluent. For some of you, it's going to be news. Nevertheless, I'm going to run through it quite quickly. So just an introduction. So probability theory today is at the basis of AI. Wasn't always this case. I mean, historically, if you think about it, probably in the late 80s, people got convinced or began to be convinced that dealing with uncertainty is an inherent part of cognition and artificial intelligence and so on. There was a big fight at that time in the AI community, and it's completely clear today the probability theory won. And there's a lot more to say than what we're going to say in this class, of course, not only technically, but also conceptually. There's a lot of other fields. probabilistic reasoning that we're not going to touch on, or almost not going to touch on, but there's a lot of stuff there. We are really using it as a tool for machine learning just to introduce the basic concepts. So what are the basic concepts? So I'm going to cover very quickly, as I said, 4 families of concepts. Probability, probability spaces and events. What are they? I'm going to remind you. Joint events, conditional probabilities, and independence. These are things that you have to understand. And if you want to understand them in more details, which you should, go to the recitation. So both today, should be Tuesday and Wednesday here. Today and tomorrow in the recitation, we're going to cover a tutorial on probabilities. Use the material that we put on the website, or use any other material that you want to kind of become a little bit more up to date on this. So today I'm just going to give a quick refresher. Okay, so the basic concept is random variables. Most of the time we're going to talk about discrete random variables. So we think about a random variable as a mapping from a space of outcomes to real valued R. Think about tossing a coin, flipping a coin. It could have 2 outcomes. It could be head or tail. Each one of these outcomes is associated with a probability. If the coin is fair, 0.5, 0.5. If it's biased, 0.6, 0.4, and so on. So x equal x represents an event, a possible outcome, and this event is associated with a probability. So you can think about many other options for random variables. And the probability of this random variable you can think about as the fraction of possible worlds in which should say A is true. Now this is an abuse of notation, and really the way it should be written is the probability that A is true is the fraction. And in general, you don't want just to see the random variable. You want to see the random variable takes a specific value to define event. Although in most cases, even in my slides, you will often not see it under the assumption that everyone knows what we're talking about. So I'm just preparing you that there is a lot of abuse of notations here. There is another abuse here, which is whether this is really the fraction of possible worlds in which A is true, or whether this is the best way to think about probability, is a big philosophical debate that we're not going to get into, but it's an interesting debate. So what are we talking about? We're talking about a universe, U, of all possible worlds, everything that could happen, and this is denoted U here. And within this U, there is an event of A being true. And the rest of it is the event that A is not true. So, what has happened? So the red oval is A is true, the rest is not A, and we know that the sum of A and not A is 1. Okay, so there are multiple ways to develop the fundamentals of probability theory. One of them is to start with Col Mughal theory that showed, or Col Mughal that showed that you can base everything on 3 simple axioms that lead to everything we know about probability theory. P of A is a positive function between 0 and 1. Valid propositions have probability 1. Unsatisfiable propositions have probability 0. And the rule of disjunction, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B, the conjunction, which you can view here in this picture. So this is sufficient for all of probability theory, and from it you can develop a lot of other things. For example, you can develop the fact that P of not A is 1 minus P of A. You can develop, and this is really important if you haven't thought about it before, or that P of A can be written as the probability of A and B plus the probability of A and not B. So essentially what we did here is we split A into two disjoint events. One is the intersection of A with B, another one is the intersection of A with not B. And together, this probability sum to A. Okay, we can also talk about multi-valued random variables. In this case, you can think about tossing a die. So A is a random variable with arity k. If it can take exactly k values, disjoint values. So I'm thinking about, and here it's written correctly, that the probability of A being Vi and A being Vj is 0. These are disjoint events. And therefore, summing over all the probabilities, all disjoint probabilities, is going to give me 1. So the probability A can either be V1 or V2 or Vk. And that gives me the sum, and again, this is the right notation, the probability of A being Vi, sum of all i's is 1. Okay, so similarly to what I talked about before, about splitting B, or it was A before, to two disjoint parts, I can split it here to K disjoint parts, and I can talk about B as B intersecting with the union of all A's, which is everything. And I can write it also as the sum of B intersecting with A being Vi. These, what's written inside the sum, are probabilities of disjoint event. All these are disjoint, and therefore the sum of the probability of this disjoint event is going to give me B again. So basically it's splitting B into its intersection with different components of A. So this actually is an important operator that is called marginalization over A. And we're going to see it in a few minutes again. These are the basics. An important thing to know about and to think about is joint probability spaces, where we think about multiple variables. Basically, you can think about it as looking at multiple variables and see how they behave together. So here is an example that is taken from the sort of the basic AI textbook, Russell and Orvig. 3 variables: alarm, yes or no; burglary, yes or no; earthquake, yes or no. And we can think about a joint probability. In this case, this is a joint probability only over 2 of the events. So what you have is 4 possible values. You can have alarm and burglary. You can have not alarm and burglary, not burglary and alarm, not alarm and not burglary. So these 4 numbers represent the joint probability distribution over these 2 variables. They sum to 1. And from it, you know everything about the probability. For example, I can ask you what's the probability of burglary, and what you will do is you will marginalize over alarm. So you'll take the sum of these 2. And this is going back to this concept that I introduced before. We marginalize over alarm. Now, we can do the same thing with more variables. Essentially, think about it as generating a truth tables. So if I have 3 variables, A, B, and C, they're Boolean variables, I'm going to write here the space of all possibilities. And each one is going to be associated with a probability distribution. So this is a probability distribution over 3 variables. Okay? How many parameters do I need to define a probability distribution over 3 variables? Suggestion? So here I defined a probability distribution over 3 variables. I told you the probability of A being 0, B being 0, C being 0 is 0.3. The probability of A being 1, B being 1, C being 0 is 0.25, and so on. These numbers on the right column completely define the distribution. Now, there are infinitely many distributions over 3 variables, right? How many free parameters define a probability distribution over 3 binary value. 7. Why 7?
Because we have 8 different outcomes that can come up combination between A, B, and C. And when we find 7, the other one will be 1.
Right. So there are 8 numbers here, but really they are not independent because we know that they have to sum to 1. So 7 of them, any 7, will define the probability distribution. So that's basically it. You understand the concept of joint probability distribution. Now, it's not the only way to represent joint probability distribution over 3 variables, and we're going to see later that there are multiple ways to represent it. Some of them make assumptions on the probability distribution. We don't even know yet what does it mean to make assumptions, but we will know in the next few slides. Here, there's no assumption. This is just a probability distribution over 8 values, over 8 configurations, represented as the values of A, B, and C. Okay, so now, of course, I can do marginalization and figure out probabilities. So here, what I know from this table is what's the probability of A being 0, B being 1, C being 0, or any other configuration. But if I want to ask you what's the probability of A being 1, it's not written in this table. You have to compute it. And again, this is the simplest way to think about this marginalization. So here is the case of alarm, earthquake, and burglary. Now it represents, in this weird way, all 3 variables. So it's split to alarm, not alarm, and within each one of them, earthquake, not earthquake, burglary, not burglary. And I can compute the probability of alarm just by marginalizing. So I'm going to sum over all possible values. This is how to read this. Sum over all possible values of B and E, the probability of alarm and burglary being B and earthquake being E, where E can be yes or no, B can be yes or no. Okay? So essentially, each element here represents a row. I'm summing up over 4 rows, if you want. B and E being 0, 0, 0, 1, 1, 0, 1, 1. That's marginalization. You can see that if I had 100 variables, I don't want to do it. Right? If I have a probability distribution over 100 variables, this would mean summing over something like 2 to the 100 rows in the table. I don't want to do it. I want to do it other ways. But the concept of joint probability distribution is still here, and it's going to be the same concept even when you have 100 variables. Okay, I can do it also for burglary. The concept is quite simple. Okay, that was number 2, joint probability distribution. You see, probability theory is very simple. Conditional probability. That's a key concept that we want to understand. So the notation is P of A given B, and it means the fraction of words in which B is true, where also A is true. So I have a universe U. Inside my universe, I have an event A, and then I have an event B that potentially intersects with A. What this notation means, care only about B. Your universe is B, and inside B, look at the part that A is on in. So, and therefore, to compute the probability of A given B, basically I'm looking at the intersection where A and B are, and I'm normalizing by B. So my new universe is B, and I'm looking at this part here relative to B. That's really an important notion. It turns out that I can write this different way, which is useful. P of A, B, and B is P of A given B times P of B. Same thing, but a useful way to write it. And this is really a fundamental theorem in probability theory, perhaps the most important one, even though we're going to see multiple variations of writing this. So this is a concept that you want to understand. And again, we can play with the same joint probability distribution from before over two variables, A and B, alarm and burglary. And you can ask the question, okay, what's the probability of burglary given that you know there is alarm? Remember that I'm abusing the notation here. Really what I mean here, the probability of burglary being on given alarm being on. Okay? And again, you can write it. This is the same formula that I've written above, and you can use the numbers and get it. You can do the same thing for alarm given burglary and so on. Okay. So here's another option. So that's conditional probability. Again, this is a deep concept, very important to understand. We're going to see a lot of it. The fourth concept that I want to introduce is that of independence. When two events, should be events, do not affect each other's probability, we call them independent. So I'm using here the notation A independent from B on the left, and that means that the probability of A and B is just the probability of A times the probability of B. That's what we mean by independent. Another way of saying the same thing, and it's equivalent mathematically, and you can prove it using the previous slide, the probability of A given B is the probability of A. So nothing changed between P of A and given that you know that B happened. It's the same probability. And really think about two dice in this case, where the outcome of what you've seen with one is completely independent of what you've seen with the other. And you can do an exercise, and I'm giving you two exercises here. You will do it yourself. Here is the same table before, only with different names for the variables, being smart, being prepared, and studying. And there's some probability distributions that is defined here, 8 numbers, because we have 3 variables, right? As before, 8 numbers that sum to 1 define this probability distribution over 3 Boolean variables. And you can ask yourself, is smart independent of study? Or is prepared independent of study? And basically all you have to do is you have to go back to the definition, take these 2 variables, and check what is the probability of A and B, check what is the probability of A times the probability of B, and see if they're the same. And this is done here. You'll do it yourself to verify that indeed the answer is yes, they're independent. The next thing which is important is to put independence and conditional probabilities together and define conditional independence. Before we said A is independent of B if P of A and B is P of A times P of B. Okay? So I'm tossing 2 coins. The probability of seeing 2 heads, if these are 2 fair coins, is a half times a half, a quarter. Right? Because these are independent. Now I want to define another notion, which is conditional independence of A and B given C. So essentially I'm adding this vertical line given C here, and the definition is going to be the same as if C wasn't here. A and B are independent given C if the probability of A and B given C is the probability of A given C times the probability of B given C. Okay, so it's really the same definition, only that I've added the dependence on C here. And this is really an important notion. For example, if we want to think about the joint probability distribution of A, B, and C, we can always say, okay, so that's actually an important notion. These 2 notions, absolute independence and conditional independence are different. It's not that one is weaker than the other. They're different. And I'll give example of that when we actually need it, when we talk about the naive Bayes algorithm that makes one of these assumptions. I'm going to give you an example that indicates that these concepts are different. Sometimes in the literature you see a mistake, and they'll tell you that one of them is weaker than the other. The important thing for us is that it allows us to rewrite joint probability distribution in simpler ways. So if I start with this probability of A, B, and C, a joint probability distribution over the three variables, I can always write it as P of A given C times P of C. Okay? If you go a few slides back, when we talked about conditionals, okay, here, P of A given B is P of A and B divided by P of B. Or you can write it this way. P of A and B, the joint probability, is P of A given B times P of B. Okay? Remember that. Fast forward to here. I'm keeping A and B here as one event, and C is the other event. So I have P of AB given C times P of C. It's the same thing that we've seen before. And that's always true. Now, and there's nothing I can do beyond that. That's the simplest way I can write this. But if you're telling me, you know what, A and B are independent given C, then I can factor it or decompose it further. I should have written here conditional independence. I can write P of AB given C as P of A given C times P of B given C, and then copy P of C. So that's the composition of this joint probability distribution, and that's going to be important. Now notice again that the first step is always true. By the way, I could have written it multiple ways, because the order doesn't matter here. I could have conditioned instead of C, I could have conditioned on B, I could have conditioned on A. So there are three ways I could have written this. They're all the same. Numerically, they're all the same. Sometimes you would prefer to write it one way over another for other reasons. For example, because you have some notion about the independence property. And the independence property, for example, here, the fact that A and B are independent given C, allows me to factor it further, which if I would have written it relative to A, maybe I wouldn't be able to do. Okay, so that's an important notion. And again, here's an example. You can ask yourself the conditional independent problem and put some numbers into it from the table and figure it out. Summary. It was very quick. I know that if you have never seen this before, it was too quick, but hopefully you all have seen it one way or another, and this was just a refresher. Everything is now at the top of your head. This is a summary of all the formulas, if you want, that you need. Think about each one of them and make sure that you agree with it and you understand why it's true. All of them are derived in a very easy way from the three axioms that I started with. But that's not really the goal here. The goal is for you to understand it. As an exercise, we'll do the following other summary, and this is a problem that is called the Monty Hall problem. I assume many of you know it. If you don't, here is the question. Suppose you're on a game show and you're given a choice of three doors. Behind one door, there's a car. Behind the others, goats. The assumption is that you prefer cars over goats, and you want to choose the door that has the car behind it. You choose a door. Say you chose number 1. And then the game, the host looks behind and opens one of the two doors, in this case door 3, and shows you that there's a goat there. And then they offer you the opportunity of switching. Do you want to switch to door number 2, or do you prefer to stay with door number 1? So who votes for stay? Who votes for switch? Okay, most of you switch, and some of you don't vote. You can all vote. So why switch? You all voted, so you have to have a reason for why you vote what you vote. Suggestions? Yeah.
Given that he opened the door with a goat in it, your chances of winning by switching are higher.
Yes. Any elaboration on this? Why is it higher to switch? Someone else? Yes?
So when you started, you had a third chance of winning. And you took one of the options with the probability of a third. But then you opened one door, and if you switched to the next door, you have a probability of a half of winning, which is bigger than a third.
So the key observation is that the host can always open a door with a goat, because one of them has a goat. Right? So your homework is to try to explain why switching is the right thing using the tools that we've developed, or at least surveyed in the last few minutes, using conditional probabilities. Try to write it down and convince yourself that that's the right thing to do. Okay, so why are we doing all this? We're doing all this because we want to talk about Bayes' rule. This is Bayes, lived in around 1763. This is when he wrote Bayes' rule. And it turns out that we actually already saw Bayes' rule, right? We saw it a few slides ago. It's just basically the product rule. It says that P of B given A times B of A is P of B times P of A given B. Or the way it's written here, P of A given B is P of B given A times P of A divided by P of B. There's nothing beyond this that now we call it Bayes' rule, and what we've done before called it the product rule or something like this. But it is the most important formula in probabilistic machine learning. So the reason we care about it is because it's very, very useful in machine learning. And the derivation is very easy. It's just what we said before. P of A given B can be written as P of A given B times P of B, but it's symmetric. You can also write it as P of B given A times P of A. And because these two are the same, you get Bayes' rule. So why is it important? It's important because it's very powerful way of modeling things. So before we get to machine learning, here's another puzzle. You have two envelopes. One envelope has some money and some bids. Another one only has bids. Someone draws an envelope uniformly at random and asks you and offers to sell it to you. How much would you pay? Had you known if there's money there or not, it would impact how much you would pay. So that's the question. Now, I'm going to give you another additional piece of information. Before deciding, you're allowed to see one bid that is drawn randomly from the chosen envelope. You don't see what's inside the envelope, but a bid is chosen randomly from it. Will that help? Why would it help? Yeah.
So the
So it provides evidence, probabilistic evidence, to whether it's the left envelope or the right envelope, right? Because it's not the same, looking at the color of the bead is going to give you evidence. Again, it's probabilistic, but it's still evidence on which envelope it is. What is the name of this envelope? So now we can compute it. Suppose it's black. How much should I pay? So let's assume that it's black and do the math here. So what do we know? We know that the probability of the winning, this is my notation here, the probability of the winning envelope, the money envelope, is half. The probability of black in the winning envelope is a half. The probability of black in the losing envelope is 2/3. Everyone agrees? Now I can use Bayes' rule. The probability of the winning envelope, given that the bead is black, my evidence, according to Bayes' rule, is the probability of being black given the winning envelope times the probability of win divided by P of B. I know that, so it's a half times some number, alpha, which I haven't computed yet. I don't know what is 1 over P of B. Okay, I'm going to denote this 1 over P of B by alpha here. Now I can do the same thing. The probability of the losing envelope given black is P of B given lose, P of lose divided by P of B, and this gives me 0.333 alpha. Again, alpha is 1 over P of B, which I haven't computed this yet. Now we can compute P of B. How would I compute P of B? Suggestions? Okay, so one way is to say, these two numbers have to sum to 1. So P of win given B plus P of lose given B is 1, and therefore I'm summing these and I can get alpha, of course, has to be greater than 1 because alpha is 1 over P of B. You can actually think about other ways of computing P of B, and I'm not going to do it now, but think a little bit about it. There is a direct way to compute P of B. Yeah. Something like that. Yeah, I'm not going to solve it now, but you do it yourself and get the same number, right? So we could have computed P of B already at the top. We just, unlike these, where it was very easy to observe, for P of B you'll have to think a little bit. So essentially, P of B means what is the probability that the bead I've drawn is black. Notice that the scenario that we're describing is there are two envelopes. Each one of them, you know how many beads are there and how many of them are black. And you know that the process is like this. First choose an envelope, and then choose a bead. Using this, you can compute what's the probability of choosing a black bead. And this is what I mean by compute it directly. Check it and make sure that you get the same number. But now we know that P of win given B is 0.4 something, P of lose given B is 0.5 something, and you can decide how much you want to pay. So that's the power of Bayes' rule. It's very simple, but given evidence, it allows you to make decisions, to make predictions. So we're going to rewrite Bayes' rule this way. This is how we're going to use it in machine learning. We're going to change A and B to evidence and hypothesis. So the probability of the hypothesis given the evidence is the probability of the evidence given the hypothesis times hypothesis divided by P of evidence. So that's Bayes' rule. So let's now decompose this Bayes rule a little bit and think about it a little bit in more detail so you'll get the intuition for those of you that haven't played enough with it. So my goal is to find the best hypothesis from some space of hypotheses H given an observed data or evidence D. That's learning. All right, that's going to be my learning process from now. Now notice, I'm going to say it several times, hypothesis here could mean many things. It could mean really a hypothesis, a function among space of functions, but it could also be a label among space of labels. So I can be Bayesian, I can use Bayes' rule in many ways. All of them are abstractly the same thing, only that the spaces are differently, and we're going to see examples for that. So what are the components? I want to find the best hypothesis, where best for me from now on is going to be the most probable hypothesis in H. Different than what we had last week, which is best was minimal error or something like this, or minimal loss. Now, most probable. In order to do it, we need to assume a probability distribution over the class H. In addition, and that's crucial, we need to know something about the relation between the data that we observe and the hypothesis. For example, when we looked at the beads before, we knew what is the relation between the observed data, being black, and the hypothesis. We knew that the probability was 2/3 or a half or whatever it was. When you toss a coin and you observe head, you know that the probability of observing head is, let's say, 0.5. Maybe there are some other models under which observing head is 0.8. So you need to have this link between the data that you observe and the hypothesis. This is an integral part of Bayes theory. So what are the components? P of H is going to be the prior probability of the hypothesis. That is my background knowledge. What I think is the probability of this hypothesis before I see any data. P of D is the probability of this sample, this evidence. It's unrelated to the hypothesis. What's the probability of observing this piece of data? P of D given H is the probability of observing the data D, given that the hypothesis is H. And P of H given D is the probability that H is the target, given that I observe D. We call this the posterior probability of H. It's the probability of H after I've observed the data. With this, I can write Bayes' theorem again. P of H given D is, I'm writing it slightly differently here, is P of D given H times the fraction P of H divided by P of D. So first of all, make sure that your intuition works well here. So P of H given D increases with P of H. Makes sense, right? So if I have a likely hypothesis, P of H given D is going to increase with it also. And increases with P of D given H. If the data is likely to occur given this hypothesis is likely to occur given this data. And also P of H given D decreases with P of D. If the data is likely, the probability that this is the hypothesis given the data goes down, because the data was supposed to be there anyhow. Okay, so what is the learning scenario that we have in mind when we have this rule which I've written at the top? So the learner considers a set of candidate hypotheses, capital H. Think about them as models. And within capital H, I want to find the most probable one given the observed data. We're going to call this most probable one the map hypothesis, or the maximum a posteriori hypothesis. And basically, Bayes' rule says this is how you compute it. What is H map? It's argmax over all hypotheses of P of H given D. Or another way, I'm replacing P of H given D using Bayes' rule. So it's argmax over all H's, P of D given H, P of H divided by P of D. Now notice that when I'm doing argmax, I don't care about P of D. Now, it's not going to change the argmax. So I can write argmax P of D given H times P of H. So essentially, what am I doing? I'm choosing the hypothesis that makes the data most likely, explains the data the best if you want, and I'm weighing it by the probability of the hypothesis. Okay, so it's a weighted sum, weighting these explanations by the probability of the hypothesis. Okay, so there are two key scenarios here. One scenario that is really important is where I actually don't have background knowledge. I have no idea what is that HI is better or more probable than HJ. So I'm actually, my prior is uniform over all capital H. So in this case, we're going to call this the maximum likelihood hypothesis. So I'm basically assuming the P of HI is equal to P of HJ for all I and J. And therefore, the argmax here, this disappears. And I'm basically going to get that it's the argmax over P of D given H. I'm going to call this the maximum likelihood hypothesis. Okay. So let's take an example. Example 1. So I'm tossing a coin. I don't know what is the bias of the coin. I have two options. Either the coin is fair or it has 60% head chance. And my learning problem is decide what is the bias of the coin. Okay? So that's a learning problem. It's a prediction problem, or it's a hypothesis selection problem. Name it any way you want. I have two options, and I need to decide which one is the most probable option. The way I'm going to do it is I'm going to collect data. This is my learning problem. How do I collect data here? I'm tossing the coin. So, so these are my two hypotheses. P of H, H1 is that the P of head is 0.5. H2 is that the probability of head is 0.6. What is my prior? I have a prior here. I really believe with probability 0.75 that the coin is fair. That P of head is a half. So my prior probability for H1 is 0.75. My prior probability that it's H2 is 0.25. Now I'm doing experiments. I'm collecting data. My first experiments gives me head. So what I want to do now is I want to know, okay, so what is my current belief? If you force me to choose now, which hypothesis is it? Is it the fair is this coin fair or is this coin biased 0.6? What would I choose now? So let's compute what would I choose. So first of all, I want to know what is the probability of D given H. This is the relation that I talked about between the data and the hypothesis. And that's really up to my model. So the probability of D given H1 is 0.5. The probability of D given H2 is 0.6. Everyone agrees with that? That's the probability of D here is tossing ahead. The probability of tossing a head, if it's the fair coin, is 0.5. The probability of tossing the head, if it's a biased coin, is 0.6. What is the probability of the data here? So I want to compute what's the probability of observing head. It's really the same question as the probability of drawing a black bead before, right? So how do I compute it? So I'm using here one of the formulas that we quoted before. You have to internalize it and make sure that you understand it. The probability of D is the probability of D given H1 times P of H1 plus the probability of D given H2 times P of H2. You have to make sure that you know this formula and how to justify it. So that's what I get, 0.525. So the probability of observing head is more than a half, which makes sense, right? Because I have two coins. One of them is a fair coin. One of them is bias 0.6 head. It has to be more than 0.5. What is the probability of H given D? This is the key thing, right? We want to know the probability of each hypothesis given the observation that we've made. So P of H1 given D, using Bayes' rule, is P of D given H1 times P of H1 divided by P of D. I get 0.714. P of H2 given D, again using Bayes' rule, I get 1 minus this, as you knew I will get. Okay, so first of all, you know that if I'm forced to choose now, I'm going to still think that this is H1, it's a fair coin. Notice that I'm a little bit less confident about it now than I was before I saw any data, right? Because my prior was 0.75 that it's a fair coin. But that makes sense because the coin was head, the observation was head, and if it was biased 0.6, it kind of pulls more to this side of head. Everyone agrees with this exercise? No questions? Okay. Now I can continue generating more data. So I can flip the coin many, many more times. By the way, before I do this, if we were using the maximum likelihood approach, not the maximum a posteriori, so I will not have prior, I will have a uniform prior, then I will now favor the biased coin, right? Makes sense, but you can verify it also with the numbers. Just do the same computation when you assume that P of H1 and P of H2 are both, the priors are both 0.5. Okay, so now I'm tossing 100 times, and I got 70 heads. Of course, hopefully, if you think about it a little bit, you will believe that the coin is biased now. And I suggest that you do the math. So I have it here. I suggest that you do it yourself. The important thing to notice here is that these coin tosses are independent. What does it mean? It means that the probability of observing two heads is the probability of observing one head times the probability of observing another head. Completely independent. And the probability of observing 70 heads in the biased coin is 0.6 to the 70. Okay? So that's the important thing. You will do the math, and you will see that overwhelmingly you believe now that it's the biased coin. Okay, so that was a simple learning exercise where what we did is we had two hypotheses, or if you want, a Boolean prediction. But really the interesting problem, as we had in the first part of the class, was when the number of hypotheses isn't finite. So I can ask you this question now. Assume you toss a coin. The coin is biased P 1 minus P. That is, P for head, 1 minus P for tail. You toss it m times, and you observe something. What is P? So this is a generalization of the previous problem, right? So before I had 2 hypotheses. Now, how many hypotheses do I have? Infinite. Yeah, P can be any number between 0 and 1. Right? So now, the simple argument that I used before of trying 0.5, calling it H1, and computing, trying 0.6, calling it H2, and computing is not going to work. I have too many P's. So I have to do something, and this will illustrate that I have to make an assumption on the relations between the data that I observe and the probabilistic model, or the probability of the hypothesis, in a tight way. We've done it also before, but you haven't noticed because it was too simple. So in this case, I tossed it m times. I got k heads and m minus k tails. What is P? So what do you think P is? K over m. Why? Does it have to be K over m? So your intuition is K over m, right? Yes?
If m is sufficiently large, you can assume that
If m is large enough, you would assume that it will be close to K over m. But you actually make one more assumption. You make an assumption on the probabilistic model. But let's do it. So I'm going to do a maximum likelihood estimate of P. How do we do it? So if P is the probability of head, the probability of the data observed is probability of D given P. I'm claiming that it's this. It's P to the K, 1 minus P to the M minus K. Okay? So again, I toss the coin m times. P is the probability of observing head. I observed k heads. So the probability of what I observed, this is a fixed sequence of m observations, is P to the K, 1 minus P to the M minus K. Hopefully you're convinced. Now, the reason this is the case is important here, because we assume a specific probabilistic model. It's called the binomial distribution. Very natural. You've seen it many times. Even if you haven't seen probability, I'm sure you've seen this. Doesn't have to be. I could suggest that the model that governs these tosses is different, and we'll give examples of that. But this is the most natural distribution to assume here, and under this assumption, this is the probability of the observation given that the model is P, that the bias is P. Now, it's easy and convenient in this case to take log in order to figure out what is P. So I'm going to take the log of the probability. It's called the log likelihood. So I'm taking the log of P of D given P. We're going to call it L of P, the likelihood of P. And that's what I get. K log P plus M minus K log 1 minus P. I want to maximize this. I want to find the value of P that maximizes this expression. You've already done it last week, for example, when you did gradient descent, so you're fluent with derivatives. I'm differentiating it relative to P. So what I'm getting is D of this guy relative to P. It's K over P from here, minus, because of this, M minus K over 1 minus P. I want to solve this for P, so you'll do the little algebra that has here. I'm going to equate this to 0 and solve relative to P. What I'm going to get is that P is indeed K over M, as you expected. So magically, what we did here is we did argmax. We didn't do argmax explicitly. We did argmax using calculus. We found the maximum of this function, which is equivalent to doing argmax over infinitely many hypotheses. And we got the right thing. So hopefully this allows you to believe in Bayes' theory now, because it gives something that you expected to see. And now you have an explanation of why is it that you say that the bias of this coin is indeed M over K. Now again, I want to warn you that we made an assumption here. It was hidden. We assume a binomial model. You could assume a different model. And then the computation is going to be a little bit different. There's one other thing that I want to finish with. So next week we're going to take this and make this an algorithm, or a generic family of algorithms, is that there's one thing we didn't attend to here, which is, and something that is called smoothing. If we have never seen, we tossed it 10 times. I've never seen tail. What do you think the probability of head is? Is it 1? Maybe not. Right? You probably want to smooth it away from 1, because it's likely that even a fair coin, and definitely a slightly biased coin, you can toss it 10 times and never see tail. So you want to do something to avoid zeros here, and we'll have to do this algorithmically. But this is where I'm going to finish today. Now we have tools, and next meeting on Thursday, we're going to use it to develop an algorithm. Final questions? Yeah?
So in our previous example, the hypotheses on the priors of 0.75 and 0.25 just arbitrarily assigned.
Yeah, I just chose it for the example. Yeah, you can choose other priors. Yeah. Okay, thanks. I want to remind you all that there are faculty interviews after every lecture, in fact, Tuesday and Thursday. Tomorrow, though, on Wednesday, in an unusual time, there is a faculty candidate, the first faculty candidate in machine learning. The talk is actually in 337 Town, 10 a.m. in the morning. And the next machine learning candidates mostly will be here. But if you're interested in this, go there at 10 a.m. Hi.
I went to the office hours last week to pick up my midterm, but they told me...
I announced last week that I'll be away. You can do it today? Today or Thursday? Yeah.
I have class at 5 p.m.
Starting at 5?
Can I email you and come at a convenient time tomorrow? Just pick it up?
Tomorrow is going to be very tough because I'm hosting the faculty candidate. I don't know when I'll be in the office and when I will not. You can come a little bit before 5 if you want.
I can, yeah.
I'm pretty sure
Monday as well,
Monday is also fine, but whatever is easier. So I'm pretty sure that I will be in the office if you try me before 5. Okay. Between, let's say, 4:45, I'll be back. But if not, you can try.
Time on Monday?
Monday.
I can just shoot you an email as well.
Yeah, I can give you some default time. Monday, I think that if you come just before 10:30, I'll be there.
Okay.
Yeah.
Okay. I'll try today as well.
Okay.
So we're wondering when can we stop by for the project discussion?
Office hours is the best time.
Office hours? Okay. So after class you're not available?
No, I have to be in this lecture that is happening here now.
Okay.
So if you come to the office hours, that's the best.
Okay, perfect.
5 to 6. 5 to 6. Always typically the same. Fine.
So I have a class from 5 to 6. So will you be available today after 6?
Today I will not be actually.
Okay.
On Thursday I will be.
Okay, then we'll meet you on Thursday. Thank you.
Sure. Hi.
Oh, I put some new bulbs in the projector. A little brighter.
You know, I haven't noticed, but hopefully they have. You know, the angle from here is not so good.
Very difficult, yeah.
But I'm hoping that they notice that. So why is it that you still have to do this menu? What's the reason?
It has to do with the emergency nature of the left projector. Left projector is a backup projector. It's the original one in there died.
I see, and we haven't managed to buy a new one.
Scheduled for a full refurb this summer. This room is going to be all redone this summer.
Oh, okay, so that makes sense, it has to wait. Okay. So what's going to happen this summer?
The latest technology, it's called lampless. It's a fascinating piece of math. Lamps cost $500 apiece. There's two of them. Okay? $500 apiece. There's two of them. That's $1,000. I just put up in that projector up there. Now there's a new player count. It's lampless. It uses a laser to sight a substrate that glows. Never burns out. So these guys are really clever. They're pricing. So they say, like, over a period of 7 or 8 years, you're going to buy this many lamps. And they price it. They price it. Mwah, right there. It's just, they know what they're doing.
And what do you think the cost of this laser is?
Oh, the projectors. Much more. Like these guys here, maybe 5,000. The lasers are like 22,000. The lampless projectors.
Yeah, no, that's what they sell it for.
That's what they sell for, yeah. But because
really,
they can sell it, because and you'll never buy another lamp.
yeah.
And it will last for 7 years, and it will never get any dimmer. Sure, fine. I'm the one who has to climb up in Halmar Hall on the top of the 10-foot ladder. You know, I'll be happy when that happens.
Good.
Hello. Check, check.
Oh, boy. I hope so, otherwise I'm going to have to talk.
Well, it's 50 minutes plus 10 minutes for questions.
My latest talk is only about 20 minutes. I did it for the the Pen Apps people. They wanted me to talk about retro computing. So they define retro computing as between the ENIAC and the IBM PC. And I lived that. That was kind of cool. So I have a lot to say about it and all the Darwinic state. I don't know, do you remember the Amiga? No. Do you remember the TRS-80? Remember the TRS-80? The Apple II.
I remember I had some Apple II.
So did you know there was an Apple III?
I think the Apple IIc, is that the color?
Yeah, that's the color ring. But then there was Apple III. So
I did
all
not.
these dead end ones. And in fact, there was a time in the late 70s when you could see that IBM was probably going to get into it. So nobody wanted to invest in like buying a computer. I was talking to my uncle, who's a research scientist at the time. I said, how come you don't have a computer? Well, eventually IBM's going to get into it. I got one of those. And they just killed off everybody else.